Joshua, take it away. Thank you.
Thank you, fellow Josh. Okay, I have a note here that says close and hit record. I'm going to do it. I'm a genius. This is the smartest thing I've done all day is write a message to myself. Okay. Hit record. 3, 2, 1. What the hell is it doing? Okay. I have that. That's on. Okay. Hi, Joshua Weiss. And yes, Josh said that I've been working on X1 plus expander, which is completely orthogonal to. That's a funny joke. You will get that joke soon. That's a very funny joke, which is completely orthogonal to what I'm talking about here. I'm just talking about here something that this is like a lab report of something that I've been working on and that I've learned over a period of time screwing around. Actually, I'll talk about that at the very end. But one of the important things, actually, this is kind of a theme. A bunch of people have come and said, I'm not an expert on this, and then given an expert level talk. Well, I am not an expert on this. You can tell me if it's an expert level talk later. But, okay, first question. I have one question to start off with. Why is this? I want that. Yeah? There we go. Okay. Does anybody know what the title of this talk is a snow clone of? Seems familiar? Huh?
There is a machine learning paper on unreasonable effectiveness.
There is a machine learning paper. Okay. Yeah, there is almost certainly a machine learning paper. This is a very commonly snow-cloned title. The original one that I am referring to is that there's a whole bunch of these. This was in 1960. There's this paper by this guy, Eugene Wigner. So, okay. The unreasonable effectiveness of mathematics in the natural sciences. Right, 1960. He actually gave this lecture 1959. If you can, it's a 65-year-old paper. You can go get it online. And if you think that it is wrong that somebody should be holding onto a 65-year-old paper behind a paywall, then you are wrong, and you absolutely should not get it on Sci-Hub. That would be wrong. That would be unethical. So I want to read you like the first paragraph of this paper, in which he says, there's a story about two friends who were classmates in high school talking about their jobs. One of them became a statistician and was working on population trends. He showed a reprint to his former classmate. The reprint started, as usual, with the Gaussian distribution, and the statistician explained to his former classmate the meaning of the symbols for the actual population, and so on. His classmate was a bit incredulous and was not quite sure whether the statistician was pulling his leg. He said, "How can you know that? And what is this symbol here?" Said the statistician, "That's pi." And so, what is that? Well, it's the ratio of the circumference of the circle to its diameter. Well, now you're pushing your joke too far, said the classmate. Surely the population has nothing to do with the circumference of the circle. And so we have all of these mathematical approaches, right? And like they do predict, the thesis of this paper goes on to say, we have all of these mathematical approaches and they do predict the natural world. But why? They don't seem like they have to. And so he takes a breath to note that as scientists, we are, quote, inclined to smile about the simplicity of the classmate's approach. But the reaction of the classmate betrayed only common sense, right? So Wigner goes on to talk about, like, why is it the case that math seems to work so damn well? And then, he spends like the rest of this discussion in total amazement more than anything else, right? Like this made-up concept. He's a quantum mechanics guy. This made-up concept of Hilbert spaces seems to describe quantum mechanics, and that they're based on complex numbers, and there's no such fucking thing as a complex number, right? Like the square root of negative. That is not right. Like that we made this up, right? We just and so. I want to hold on to this amazement that Wigner comes in here with. And I want to talk about an algorithm and a series of concepts that I find to be shockingly amazing at solving like every telecommunications problem that we have. This thing is the Fourier transform, not the Fourier transform. I'm told that that's more different. I'm told that I had to make that joke. I presented this at the Mountain View Reverse Engineering meetup and said, dude, I don't care. Like I do care about your talk, but you have to make a furry joke, and there you go. But okay, so you are not expected to understand this, right? Like I'm presenting this. Which what? Is that Tumblr key smash? What is Tumblr? That's right. That's correct. Every time I've opened up one of these, every time I've opened up a textbook, like especially on error correction codes, right? The first page is like, here is XOR, and the second page is like, I opened up LaTeX. Anyway, so what I want you to know about this is that it relates the frequency domain representation of a signal with the time domain representation of a signal. We'll talk about that in a minute. But this works for any kind of signal. Hopefully, we're not going to go into a whole lot of math here. Hopefully, this is actually going to be, I hope this is going to be the last time you're going to see it today. And the only reason I even present this equation for you is to ask, what the fuck is that thing doing up there? We were talking about signals. We were talking about signals. Where are these circles? So anyway, this talk is for a very wide set of audiences, and not everything is going to be for like some people are going to go like I know all of that blah blah blah, and some people are going to go I've pushed. Most people are intended to come away with slightly more knowledge than they started with, and then a bunch of ideas to think about in the back of your brain with. I'll get to that later, but if there's something that doesn't make sense, don't give up. Don't feel bad. Do tell me later. But if you get slightly more than you came in with, there should be a point at which everyone gets lost eventually. That's my hope. It's different for every person. That's the goal. So basically there are kind of three things that I wanted to talk about, right? I said that the Fourier transform relates the frequency domain to the time domain, and I think we should just do a little bit of an intuitive overview of the frequency domain. There's this concept called OFDM. That's actually what I really want to tell you about, and I want to tell you about why the frequency domain makes it possible to have the concept of OFDM at all. And then I want to tell you how OFDM solves every single problem we have ever had, and then you are all going to be experts, and it's going to be great. So I want to start looking at some signals here. This looks like a sine wave, right? This looks like a sine wave because it broadly is. And there's a couple of different ways that we can talk about this, right? This has a period of 1/4 the sampling window. Wait, hang on a second. Do I have a... You come here. No, I can't hit that with a laser. This has a period of 1/4 of the sampling window, right? This is the period from here to here, right? Another way that we can talk about this is that the frequency is 4 times the sampling window, right? I didn't say hertz here because nothing in here says seconds, right? Hertz is 1/seconds, right? And finally, the last thing that we can say about this is that it has a period of 512 samples, right? And we can look at it. We can use our eyeballs to look at it and know that there's one sine wave in there. And so if it's roughly true that you can decompose any signal that fits into a given bandwidth into a sum of sinusoids. A sinusoid is a sine wave approximately that has been shifted or scaled or, right? So it's roughly true that you can decompose any signal that fits into a given bandwidth into a sum of sinusoids, sure. And if we look at all of the sinusoids that fit into this bandwidth here, right? Here's a list of all of them. We can see that one of them, just one of them, has an amplitude of more than 0. It's hard to see. Let me zoom in. And if we zoom in on the frequency content, then we can see that this is, in fact, a frequency 4 sine wave. And just as a reminder, so that makes sense, right? And so let me just go through a quick reminder of some of the other properties of the frequency domain. When we add 2 signals together in time, right? Here are two very different signals. Here they're both sinusoids, and they both have one frequency component there, right? If we add these 2 signals together in the time domain, then it's the same as adding their components together in the frequency domain. That make sense? And right, I just want to. Oh, right. Here's the other. This is the other really important thing about time domain, frequency domain. This is actually really, really important. One more idea is I'm just going to show you with one sine wave here. But if you take a signal and you add together a couple of copies of that signal, that are only shifted in time or scaled, right? So these are the same frequency. They're just shifted forwards and backwards in time, or they're bigger or smaller. And you add them together, then you get a copy of that signal that has been shifted, a copy of the original signal, right? That has been shifted in time and scaled, but has no new spectral information. Okay? There's no other frequencies that have magically appeared. And this is the case for any repeating signal that you can come up with. The exact way that any given frequency gets pushed around is different for any frequency. And so if I shift a whole signal by time and add it together, each frequency in there will get changed slightly differently. But no new frequency gets added, right? So here's another version, right? I've taken this, and again, two different signals, and they have the same spectral content. If you look at the phase of the little guy with respect to the big guy, the larger wave, that phase has shifted a little bit, but there are still two and only two sine waves in the output, right? And also, this is knowable, I should note. We're not going to say what, I'm not going to say here what it is that makes it knowable. But for any given combination of a delay and shift of signals that you're adding together, and any given frequency, we can know what the effect will be on any given frequency in the signal. Okay? That makes sense? This property, we're going to come back to this property. This is a really powerful concept. And the idea is that we give a name to any transformation of a signal that looks like this. If we add up a bunch of shifts and adds and delays to a signal, that's a linear time-independent transformation. Linear, why is it linear? Because adding is, so if it happens, multiplying is adding multiple things together, right? That's linear. There's no square root. There's no component there that depends on the amplitude of the signal. It's always the same. Time independent, why is it time independent? Because if I do it now, if I do it in 2 hours from now, the same thing happens no matter what. And importantly, if I do it now, if I do it in 1,000 samples from now, the same transformation happens, right? And if you're a nerd, then this thing can also be represented with a thing called a convolution. And if you don't know what that is, that's fine. Oh, yeah. And speaking of nerds who are going to well actually at me here. You're noticing, if you are such a nerd, you are probably noticing that I'm talking about real numbers here and not imaginary numbers, whatever those are that are made up. And that I'm talking only about amplitudes here, but there is actually a phase component here. And so the reason why I'm doing this is because it is easier to visualize this with the time that we have, right? To visualize only amplitude. But all of these transformations that I'm going to talk about that apply to amplitude, they apply to phase also. So if you're going to stop me and tell me about this, anytime you can just take a breath. Anytime I say multiply the amplitude, imagine that I said rotate the phase. And if you hadn't known this was a simplification I was making, it's a sound simplification approximately. Don't worry too much about it. And oh yeah, there's a transformation between time and frequency domains, right? Okay, so so this is what we just talked about. There's a time transformation between time and frequency domains. When we make certain transformations, they have other predictable transformations in the frequency domain. We talked about that. And oh yes, that transformation between time and frequency domains is sometimes can be really fast and efficient. If you looked at that Fourier transform that I showed you before, and saw that big sigma in the middle, you're like, huh, that's an O of n squared. Well, there's an O of n log n algorithm. So there's a way to do this really efficiently. That's out of scope for today. Anyway, let me show you some more interesting signals and like how we transmit data and what that looks like in the frequency domain. And so this is, depending on who you're asking, this is either an NRZ code or a BPSK code. And I'll call it non-return to 0. We are just transmitting bits 1 bit at a time, either -1 or +1, depending on the bit that we are trying to transmit. And we are transmitting it well below the frequency limit of what we are capable of seeing, right? There's many samples per one single bit, right? And as a result, we see this repeating pattern in the frequency space. We are only using this much of our frequency space to actually transmit data. Does that make sense? Um, so so more concretely, we would say the baud rate of this is below the sampling rate. And to make this a little bit easier, we're gonna look at amplitudes for the rest of this time. We're gonna look at amplitudes logarithmically, since rather than adding or subtracting most of the time, we're going to be multiplying, right? We are going to be scaling things in linear time independent transformations, and so that all is multiplicative, and so it's easier to visualize that logarithmically. I want to just kind of show how various transformations impact a signal. Are we familiar with what an eye diagram is? Eye diagram shows us how we can distinguish between whether we're receiving what we were transmitting, whether there is space between being able to tell the difference between a 1 and a 0. And so this eye looks really good, right? There's a big difference between 1 and 0. And so the eye here is wide open. There's a dot, dot, dot in the middle, right? And so what happens if we introduce a channel that performs a little less well at high frequency? Here's this impairment that I've added on this channel. The channel rolls off like that. And in this case, the eye still looks just fine, right? We have no issues telling the difference between a 1 and a 0. Definitely happening there, right? Let's introduce a channel that performs even less well at high frequency. The eye is still open, right? We can still see, like if I sample right here, I can tell the difference between 1 and 0, right? And if I have a channel that looks even less good than that, that's not looking great, right? This is a transformation that we cannot fit a simple equalizer to, right? I can't just go I can't just go pre-emphasize this and put my high frequencies back. And you're going to say, Joshua, that is not what real channels look like. And I will say, yes, they will. Antennas, this is like completely reasonable for something that happens in an antenna or elsewhere in a system. But one thing that's worth thinking about here is that, again, if we're just looking at the frequency domain here, right? These are all linear time independent transformations, right? We decided on that. And so therefore, these linear time independent transformations also happen. These signals are the same, right? These are two ways of viewing the same thing, right? So if a linear time independent transformation happens here, it happens here. And if these linear time independent transformations happen to happen, like if these happen to be how we model the real world, and if it's easier to reason about transformations in the frequency space than in the time space, then why don't we take our data and put it in the frequency domain rather than in the time domain? And in some senses, the data is everywhere, right? It is in both domains at all times, right? It is two representations of the same thing. But if we start thinking about our data as being in the frequency domain, what would that look like? I had 256 bits earlier, right? And now I've put the data into the first 256 frequency components. Okay? The rest of the frequency components are 0. And so, by the way, you remember that we had this kind of like lumpy structure where we were using all that spectral space, and we weren't really doing anything with it previously, right? We'll come back to that later, but I'm just going to zoom in on this so that we can see exactly what's going on, right? I'm using this coding here, and you can see, okay, so here's 001, 00, right? I can see where I've stored my data there. And the inverse Fourier transform, I'm looking at this, if I plug into an oscilloscope into this, I'm no longer seeing zeros and ones. An eye diagram does not exist for this anymore, right? Well, in some senses, right? The eye diagram in the time domain is nonsensical. And that's fine. The data are still there because we can see them in the frequency domain, right? And if I receive this signal, right? Let's say I'm adding, I don't know, 0.2 peak to peak of noise. That's what I think that's what I added here. 0.2 of peak to peak of noise there. and so that's like -8 dB worth of noise or so. And if I convert that time data back to frequency domain data, and so I'm just going to put this simple threshold here, right? So one, you can see that I've added some noise in the higher frequencies where I was transmitting nothing, but where I'm transmitting data, I can still threshold it, and I can still recover all of the data that I've transmitted, right? And so this is a super duper powerful idea, and it is so powerful of an idea that they gave it a name. It's called OFDM, and this is what I wanted to talk about today. And it's the foundation of a huge number of modern telecommunication air interfaces. Okay. LTE, right? Cell modems, that's reasonable. That's definitely an OFDM air interface. Wi-Fi 6, okay, so they got around to OFDM recently. 5G, that's an evolution of LTE, we're good. DVB-T, who knows what DVB-T is? Yes, that's European Digital TV, right? And they decided they're going to use OFDM. The Americans, we have decided that we are going to transmit using 8VSB, which is this weird halfway thing where you do amplitude shift. Oh, no. In the most recent version of the spec, we changed to OFDM also. Let's see, DOCSIS. And what's DOCSIS? Cable modems. What's that? Anybody know what that is? That's a DSL modem. DSL modems are one of the very first uses of OFDM in consumer products, as far as I understand. And it makes sense, right? Because the whole problem with the DSL modem is that you have an absolutely garbage tier channel, right? You have just an absolute trash channel that is uneven between you and the central office, and you want to cram as many bits over it as you can, and the impairment is somewhere in frequency, and so you want to figure out what that impairment is and then cram as many bits over it as you can. And so what does OFDM stand for? OFDM stands for Orthogonal Frequency Division Multiplexing. Well, what? Yes, that's right. Good. That's right. I am very, very funny, right? What's frequency division multiplexing? This makes some sense, right? We are going to take a bunch of bits and we are going to multiplex our data by frequency. Multiplex, divide it up by frequency. Frequency division multiplexing. Orthogonal. Does everybody know what orthogonality is? Like, I have these two axes, x and y, and if I move along x, then the y coordinate does not change, right? X and y are orthogonal to each other. If I, for some godforsaken reason, define my axes like this, x and y, a change in x results also in a change in y. If I move something along the x-axis, it necessarily changes along y. X and y are not orthogonal, right? So when we choose frequencies to divide on, we choose frequencies that are somehow orthogonal to each other. If I put some content on this frequency, it doesn't change anything else. And this is this is a little bit like in some senses this looks intuitive, right? But in some senses, the careful choosing of these frequencies really matters. In this example, I discretize all of these frequencies, right? I say that the frequencies are allowed are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? But in reality, we know that we can have there's no reason why we can't have a 2.5 hertz signal, right? That's legal, right? And so the answer is that those, like the frequency space is contiguous, but some of those frequencies, if we go and sample them and look at them like this, they will cause things to show up, especially over a finite window. They will cause things to show up on other frequencies, right? We are looking at this only over a finite window. So depending on how you look at it anyway, the frequency space, the orthogonal frequency space is discretized. And so how do we choose which frequencies that we are allowed to transmit on? There's one particular transformation that makes it easy to separate out these frequencies. What is this transformation? It's the Fourier transform. And so by the way, when was this idea, like we had this explosion of technology starting with like DSL modems, so you would think like we came up with this in the 80s, right? No, hell no. We filed, for those of you who are squeamish when you see a patent, which you should be, Your party line should be I don't read patents. If you've never heard of the words treble damages, you should go look them up. But in this case, I can tell you this patent is solidly expired. So you're good. And oh yeah, what's the one other interesting thing here? This is assigned to Bell Labs. Everything good came out of Bell Labs. Okay, I have right here's one more aside for nerds. And so I mentioned also that I am truncating complex numbers and just looking at their real components, or just looking at amplitudes and like doing some aggressive lying about the contents of things here. And you may be looking at me and you're going, Joshua, this is a very bad representation this is a bad way to encode a signal on an OFDM frequency. I'm not actually doing on-off keying or anything in particular. I'm choosing this weird amplitude shift keying that is hard to really tell the difference between. And I will say, the way that I've chosen to encode things on each frequency is not good. You should not do this. But it does work, right? And more to the point, it is easier to see. I can put a nice line for a threshold there on screen. Okay, so when the reality, again, for those of you who want to go deeper into this later, like you might choose to use PAM4, you might choose to use PAM8, you might choose to use a constant power level for BPSK. This is not a constant power level across the spectrum, so you're wasting some transmitter power, blah, 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 blah. Anyway, just all this is to say, this is not really how you do it, but it's a good way to demonstrate it. Okay, so what have we talked about? I promised you we were going to talk about the frequency domain. I promised you that we were going to talk about how we were going to use it with OFDM, and now we are on to the fun part. So what did we come to? What's the insight that we came to earlier? The things that happen in the real world are mostly linear time independent transformations, right? Linear time independent is adds, shift, multiplies, right? And those are a lot easier to pick apart in frequency space than in the time domain. And so let me give you a couple of examples of the sort of problem that OFDM solves. So let's come back to this example we saw earlier, where we demodulated a signal that we received. This is fantastic in the ideal case, right? I'm a happy camper if everything goes well here. But if the signal has like some kind of weird channel fading, let me show you. Let's bring in that channel fading that I saw before. This threshold no longer gives readable data, right? If I choose this threshold, I'm going to see a little bit of a bit error rate on these channels, and here I'm getting it totally wrong the entire time, right? Right, yeah. So again, I said like it's not obvious that actual channels have loss that looks like this, and it might not even be obvious that the channel loss is relatively smooth. That is to say that it's not scattered differently on each one. Trust me that it is, and it's out of scope to say why, only to say that, shockingly, it has to do with the Fourier transform. So I want to compensate for uneven channel fading. And the way I want to compensate for this is I want to somehow measure the channel to see how it's behaving. Right? Like I want to know what the shape of the fading in the channel is and what I need to compensate for. And so the way that a bunch of OFDM implementations do this is by inserting specific subcarriers. Does everybody understand what I mean by a subcarrier? One of those channels is a subcarrier. And they're going to insert specific subcarriers that have what they call pilot tones. I raised these pilot tones here to make them a little bit more obvious. That have specific pilot tones that are, and we know both on the transmit and the receive side which subcarriers have pilot tones, right? And so since we know on the transmit side and we know on the receive side, we can measure the pilot tones on the receive side and compensate inside the receiver. So I'm just going to linearly interpolate my threshold between these. And I moved the threshold here, by the way. Previously, I had it right in the square in the middle logarithmically, excuse me, to make it easier to see. I moved it to be equidistant linearly because of the way that, because that's how it should be. But right. So and you can see now that I've changed this threshold to interpolate based on where the pilot tones that I've detected are, I'm actually recovering basically all my bits. My error margin there is not fantastic. So maybe this isn't quite enough pilot tones for the fading that I'm seeing in this signal, but that's pretty good. And so I want to talk about like another impairment then. Let's say that I add some burst noise in time, right? How did this happen, by the way? Huh? Lightning strike, yes. Lightning strike here is totally a good option. I was thinking another good option was like an airplane flew over between me and the satellite just in that short period of time. For whatever reason, the amplitude was reduced by half during those couple of samples, during that orange period only. And so, okay, because the entire thing goes into everything, right? Is the whole symbol corrupt? Well, this, by the way, is not an error that is linear and time independent. This is not time independent because it depends on time, right? So OFDM is not designed to compensate for this. But it turns out that this is actually very recoverable, right? The noise is distributed across all of the symbols. And in fact, if I was looking only in the time domain on here, if these samples were corrupted in a on-off keying pattern or something like that, right, then I would have lost those samples entirely. So in this case, my bit error rate is a little high there, but other than that, I'm doing pretty good. Oh, and so when I said earlier that like this is a bad modulation, right? You would not actually want to do this in reality. This is why, because the lower amplitude, the zeros are corrupted more than the ones are, right? And so I would really ideally have a constant amplitude modulation. And again, so if you're thinking about that kind of thing and like, oh, why would I choose BPSK over on-off keying or something like that? And you know what those things are, then that is why you might choose that. Okay, I want to move on to another impairment that could happen in reality. It's all good when a signal goes from one place to another place, right? We send it, we receive it. The real world's a little more complex. And we have multipath reception. No, multipath reception. So, okay, in the real world, signals can bounce off and reflect, right? Was that joke funny? Yeah, okay, good. I thrive on your acceptance. So multiple copies of the signal show up. I even made the green arrow a little bit smaller, right? Multiple copies of the signal show up at different times and with different amplitudes, right? And if we look at these three signals that are being received together, they sort of look like this. And we could sum these together, by the way, to represent what we receive, right? And if we sum these together, these are summations of adds and shifts. What do we call that? Linear time independent transformation. That's right. Which we already proved is possible and easy to fix with the magical power of the Fourier transform, right? We just did that a minute ago. So there is at least a little bit of a problem. And that is that these signals don't exist in a vacuum, right? Each of these things that we did an inverse, so in order to generate this signal, we did an inverse Fourier transform. That's how we got that. Each of those block of samples that we call a symbol comes one after another, right? So like in reality, this thing happens here, right? And these red regions are a different block of symbols than the one that we're talking about. So this is not actually a repeating symbol in time, right? If this were a repeating symbol in time, we would be good. But this is something completely different. And so we start delaying the symbol. The old symbol overlaps into the new one. We always have to sample exactly the same number of samples each time, right? We're always going to sample 2048 samples. So no matter where we choose to sample, we are going to get one symbol blurring into another one. Oddly, we call this intersymbol interference. So the elegant OFDM, right, okay. Right. Okay. The elegant OFDM solution to this comes from something that we saw before. And we know that these signals are supposed to be, in order to get, to recover from intersymbol interference, we know that these symbols are supposed to be repeating in time, right? Any shift that is repeating in time, we can recover from, right? And so since they can be shifted forwards and backwards, they can get shifted in a loop. So if we want to add something to either side of the symbol to space it out effectively, we know what we need to add, right? We take the end of the symbol and just add it back to the beginning, right? Does this make sense as to why we can extend a symbol in that way? Yeah? You are losing efficiency. You are correct. So that is 100% the case that you are losing efficiency, and indeed you are losing efficiency by adding pilot tones. And so what do you get for your losing efficiency? You get the ability to recover from multipath, right? So okay, but so indeed, and you can choose, by the way, you can choose how much multipath you're willing to recover from. In OFDM parlance, this is called a cyclic prefix. We take a chunk from the end and we add it to the beginning of each symbol. And you can choose the size of your cyclic prefix, and in fact, this is encoded in, like when you, in DVB-T, for instance, they have some pilot header, or some pilot channels that they encode all of that information on. Anyway, right. So when we receive, we still receive the same region each time, or the same length each time. Sorry, and we choose to receive the region in between the red lines, right? And that region only has information from this symbol, from some position in the symbol in it. So there's no intersymbol interference. By the way, how do you know where to receive when there's one symbol after the next, right? When you're not actually just repeating endlessly in time. Like, how do you choose where those red lines are? The cyclic prefix helps you align to that, right? Because you know that these data ought look like those data, right? And so if you, the advanced version of this, right, is that you do an autocorrelation in time, and you want to figure out when you saw something that you saw approximately the right time ago, and if you see the same data twice, then you know you're aligned. Two birds with one stone, right? You solve both. Yes? Yes, wouldn't multipath possibly make that correlation impossible? So your cyclic prefix had better be a little bit extra long then. By the way, being able to do this gives you two things at once, like or three birds with one stone, I suppose. There's this cool paper, this algorithm that I really don't understand, that not only helps you detect the correct position in time in a symbol, but if you have a frequency offset, like maybe due to Doppler shift or something, you're receiving on the wrong frequency, this algorithm can estimate both. Oh, that's maximum likelihood, not machine learning, you goober. Anyway, I don't understand this algorithm at all. You can go read this algorithm. If you understand this algorithm, you should definitely let me know, because I solidly do not. So anyway, now having done this, I'll have, by the way, feel free to take pictures, no problem. There will be a QR code at the end with resources for all of this. And so what do I get if I go recover this multipath signal? I chose shockingly high amplitude on my multipath to make this visible. One of those echoes is -3 dB of the original signal. That's huge. Huh? Yes, right. That's half the strength. That's half the strength of the original signal. And so even still, so there's corruption. There's a repeat with half the strength of the original signal, and OFDM still recovers from this with a small number of subchannels corrupted. Okay. So this is more than good enough for, again, coming to the question of, do we want to trade off efficiency to get, do we want to somehow trade off efficiency in order to get more recoverable data? If we layer an error correction coding scheme on top of this, then we will trade off some efficiency, but we can now recover those small number of subchannels. Or if I wanted to be more resilient against this, I could add more pilot tones also, right? And so The other good thing to note about this is that if your error correction scheme is a soft input or soft decode scheme where it's not just 1 or 0, but you know that, oh, I'm confident about this bit, I'm not confident about that bit, and you can factor that in. These are, like, we know which of these we don't know about, right? We know that we're basically right here, and we know that we're not so certain there. So this is the kind of thing that we're making it pretty easy for an error control scheme to recover from. I could go on for like hours and hours and hours. I'm going to give you one more of a interesting concept, and this is the thing that is really most mind-blowing for me for about OFDM. And so earlier I showed you this, right? I showed you this slide, and one challenge in radio technology is that we want to occupy exactly as much RF bandwidth as we need, right? We don't want to transmit more. We don't want to, like, if we're occupying all of this spectral space, right, we don't actually need that. That's space that could be used to transmit something else, that somebody else could use. And so that square wave requires a lot of bandwidth with all the spectral replicas, and I'd like to filter it, right, but it doesn't really exist. Like, you can't make a brick wall filter. The thing that I would want here, like, allows this, and then everything else below that is negative infinity. Brick wall filters don't exist. And so in reality, you end up not filtering out enough of the stuff that you want to get rid of, right? Like, if I apply a filter that looks like this, and I allow myself, okay, up to 30 dB, then I'm still using nearly 4 times as much spectrum as I need to. Or I could filter more aggressively, and I end up affecting the stuff that I do care about, right? That would be bad, right? Now I'm losing this, and we saw what happened in that eye diagram earlier. Or the reality is actually that we end up doing both, right? We filter out the stuff that we care, like if I try and filter that, I'm going to filter out the stuff that I care about, and I end up not filtering out enough, and I still end up using a whole bunch of spectral occupancy. So the cool thing about this is that OFDM solves this in a sense. I can make my Fourier transform as long as I want. This is solved by construction because I am only occupying this much bandwidth, right? And somebody is going to tell me, you would be correct to tell me, by the way, that if I put this through a digital to analog converter, I am going to get spectral replicas way out there, right? But I need a filter with a much lower Q in order to do this, right? I can filter all the way along here without worrying about affecting the parts of the channel that I care about, and I might be able to deal with any of those effects on the parts of the channel that I care about, right? Yes, right. There's spectral band replicas way out there. Okay, fine. But oh, I already said this. Fantastic. Well, there you go. That's a graphical representation, right? I can set up a filter like that, and I can choose my FFT to be, or my Fourier transform to be as wide as I want, and use as many subchannels as I want to provide the guard bands that I care about, and use less spectrum. And so this is really cool. And here is the thing that that brought me to really give this talk, which is, let's say the other side of this is also true. Okay? Let's say that I am a ultra low power cellular modem, and I only care about a couple of channels at a time. I'm an LTE Cat-M modem. I only care about a couple of these subchannels in the OFDM signal. And I know, like, the cell tower told me in advance, I only care about like that channel in there, or like 7 or 8 subchannels. I can apply a filter that picks those bands out, and now I have fewer subchannels to work with, and I have an even smaller Fourier transform. I don't have to do a size 2048 Fourier transform on this. If I filter those frequencies out, I can do a Fourier transform centered on these frequencies, and I can use a whole lot less energy to receive only the data that I care about. And I can do this without compromising the ability for the cell tower to transmit a wide Fourier transform to everybody's cell phone. I'm seeing quizzical looking faces. Where is the free lunch? Well, you have to make that filter really carefully shaped. You have to be really good at making that filter. But indeed also you have to schedule, you have to choose which subchannels you want to schedule on in order to make this happen, et cetera, et cetera, et cetera. It's not totally a free lunch, but like this is the kind of thing where like this happens to fall out of this algorithm. This falls out of this basic concept. That is why this is so exciting to me. I could go on for hours about this. There's so many cool things I don't have time to talk about. I'm going to seed you with a couple of ideas for things that you can go look up later. You can, or just think about them in the back of your mind. So what happens if your local oscillator shifts, right? If your local oscillator is drifting a little bit, then you can use the, we ignored phase so far, right? But you could use, that has a phase transformation on all of your pilots, right? And you could use the phase data from your pilots to shift your local oscillator back to where it is supposed to be. Or if you have Doppler shift, which means that your sample rate is effectively inaccurate, it's local oscillator shift, except all of the pilots move slightly differently, and you can compensate for that with again by servoing all of your control loops that way. Let's say that you have a diversity of receivers that have different decode capabilities, and you want to be able to transmit data on the same chunk of spectrum for both high-power cell phones and low-power cell phones, right? You can devote different subchannels to different modulations. This is not a thing that I can do if I was just transmitting symbol after symbol after symbol after symbol. There are not really receivers out there that like, oh, I'll look at every third symbol and try and do clock data recovery on every third symbol with BPSK or what, right? Like, and determine if it's QAM or not. You can't do that unless you have many subchannels. And similarly, if you actually want to go the other direction, let's say you have a room full of cell phones and you want them all to transmit back to the tower at the same time, you can give them all subchannels on the, you can give them all, assign them each their own subchannels to transmit back to the tower, right? And then you can equalize each of those independently. And so everybody can transmit at the same time without having, as long as they've been assigned subchannels in advance. Everybody can transmit at the same time. Again, this all, these are, if this doesn't make sense now, think about it for the next 10 years or so. That's what it took me. And I should say OFDM does fix almost everything. I'm running low on time, so I'm not really going to say much about this. But like, if OFDM doesn't solve all of your problems, you can consider various cross-interleaved error correction codes. And in fact, this is what people do in reality is if you want to spread data over many different symbols, for instance, and if you want to use the problem with Reed-Solomon BCH codes, again, is that you can't, that you basically have to do hard recovery. And okay, let's say that you have information about like, oh, I think I got it, I think I didn't get it, right? If you have that information, you can pass that to a convolutional code. So here is what we talked about. You are all experts on thinking about things in the frequency domain now. You're all experts conceptually on OFDM. That's all really good news. And you actually have enough information to go implement it yourself. And so I said in advance, I said previously that I'm not an expert. And this has been this talk is 16 years in the making. In 2005, this French madman, the people who laughed, this is because they recognize the name Fabrice Billard, who is the guy who wrote FFmpeg and QEMU. Right, yes, the same guy did both of those, right. And he also happened to just release this file. You display it on your screen, and you connect an antenna to the green pin of your VGA digital to analog converter. And then you wire that to your television, and the spectral replicas from that happen to show up on the right frequency for television and form a valid DVB-T signal. And it works. And I saw this and I went, what the fuck? And I went, this is in 2009. I had just taken a Intro to Signals and Systems course in undergrad. And I went, I obviously now have enough knowledge to decode this. And you know, so this was in 2009. I started writing some visualizers, and that's not really what a QAM constellation looks like. I was seeing approximately noise. And you can tell by the change in Mac OS that a decade later, I finally I was on an airplane home back to Boston late 2020 when I finally managed to lock the synchronization of what he had posted on the internet however many years prior. And decode this. So this has been 16 years of working on this and learning about it the hard way. You don't have to be an expert either in order to learn these kinds of things. I want to come back to kind of the namesake for this talk, just to close with. Wigner's concern at the end of his paper was that, like, we might not always be this good. He said the level of knowledge and ingenuity is a continuous variable. And, like, you know, to the extent that we might have gotten lucky so far, right? Like skill problem, well, skill solution. In the future, it might be skill problem, right? And his concern is that our suddenly consistent world, like, starts to break down. And he has this concern about how lucky we've gotten with all of this. And I'm not sure that we got lucky with the concept of the Fourier transform. Like, in some senses, that is really by construction. Though I guess it is lucky that sine waves are orthogonal to each other. But we sure as fuck got lucky that the fast Fourier transform is in O of n log n rather than O of n squared, right? In the resources for this, there's this YouTube video that you should watch if you have 25 minutes and you want to think about this that explains how to construct the fast Fourier transform. I watch it like once a year and I understand a little more each year. Anyway, Wigner concludes to say, let me end on a more cheerful note. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that it will extend, for better or for worse, to our pleasure, even though perhaps to our bafflement, to wide branches of learning. There's a lot of fields like that out there. There's one out there that's getting all of the press that we don't really understand, that seems to be talking about using bizarre, complicated mathematics to make consciousness or make a godhead out of or whatever it is, right? But all of this has been there all along. And even for, like, the Sparkies amongst us who want nothing to do with this AI shit, we have plenty of opportunities to express wonder at the kinds of research and development that have been done, like, since Bell Labs did this in 1960, right? Applying big math to our work and getting these, I don't know, I think these are kind of beautiful results. Like, this is an almost intuitive result. If you look hard enough, it's intuitive, right? And so I think my claim also is that, like, it's probably worth taking a moment to revel in it a little bit. Anyway, thank you all. I think we have like 3 minutes that I can take a couple of questions. Here, that there is a resource set there. I hope these slides will show up eventually. I mean, the slides are there, and I will post these to my internet. Yeah, does anybody have any questions or want to correct me? Yeah.
Do you have a sense of why does it make more sense to
why did it take so long for us to come up or to actually use OFDM if Bell Labs came up with this in the 60s? And I think part of this is how wide of a Fourier transform we can efficiently implement now. And also we've gotten better at implementing. So one is we have more compute power to do wide Fourier transforms. We've gotten better at implementing Fourier transforms. Like the faster Fourier transforms have gotten a lot faster. Like if you think about the IEEE paper that I posted a link to that explains how to do offset and carrier recovery, that's a relatively new thing. But also, this was the early foundation of DSL, right? So it is somewhat old in that regard. And you could see the evolution of this then. If you think about dial-up modems doing the right, the training sequence, then when they would make wideband spectral noise and then try and measure it on each side, then that was in the DSL times. That is what they did. Is they did pre-training to bring up the link, and after they brought up the link, then they would not continue to have pilots or anything like that. They would just assume that the link was constant the whole time, and so that is in some senses an evolution that happened, and the subsequent evolution of DVB-T being low enough power, being able to do a Fourier transform in low enough power that you could do it with mobility and that you could do constant measurement of the channel, that came as we were able to do Fourier transforms in lower power. So it did take a while, but yes. Yes?
So I wanted to ask you, what are the limits in the sense we still miss packets and we still miss the, the communication fails in between. At some point, we are not able to recover the signal from this OFDM, right? At what point we cannot recover the lost signal?
What point can we not recover a lost signal, or what are the limits of what we can recover? That's a great question. And so if I come all the way back, I'm not going to be able to find the slide, but if I come back to that slide with the threshold there, right, and being able to tell how much noise we can add, that fundamental question is called link budget or link margin, right? How much noise are we able to add before we can't recover anything at all? And so the two questions about that are, one, when do we lose the control integrity of the signal? That is to say, like if we can't recover where the symbols start and end, it's definitely all over. We are not seeing shit, right? And on the other hand, if we manage to align to symbols and we cannot recover subchannels, then now we have a noise margin per subchannel, right? And so to the thing that I had mentioned previously of having multiple different modulations in a single OFDM carrier, actually DVB-T is a great example of this, because they have on their pilot frequency, or on their pilot subchannels, they phase shift back and forth to transmit a very, very low data rate control signal. They say like, hello, I'm a DVB-T signal. You should expect my pilots here. We are at location X in the sequence of scattered pilots, et cetera, et cetera. And that is designed to be recoverable roughly, no matter how bad the signal is, that there is something there, even if I can't recover an MPEG-TS data stream out of it. So you can have multiple modulations to increase the receivability of the signal. Does that make sense? Yes?
You mentioned the problem of spectral reflections and not being able to make a control filter. Can't we do that if we stay in the frequency domain and just multiply them times 0?
Can we do a frequency domain spectral filter? Yes, but it starts to be, now you've lost all of the benefits of transmitting in the time domain. The whole benefit of transmitting the time domain is that you don't have to do a Fourier transform.
His objective is to maximize bandwidth, but that's not solving the problem. It's like post-process.
Right. Yes, you could have a very good filter, and it could be a very expensive filter. But if you already have to shift into a digital representation of frequency domain data, but yes, you can do that.
Yes. Yes.
If
if we assume the channel is not changing characteristics too quickly, could we have a pilot tone be here, then next time here and here, so I'm not wasting space for all those subchannels?
Yes. Can you, if you assume that the channel is not changing quickly, can you move the pilots around? Yes. That is called scattered pilots, and that is what DVB-T does. The idea is that there are some constant pilots, and then they have they know what offset into, it's symbol 1 through 6 in a super frame, right? And you know that at symbol 1, you get this set of scattered pilots. At symbol 2, you get this set of scattered pilots. And so you get effectively more fine-grained channel measure or characterization while using fewer pilot tones for that. Yes, that is a good insight. And indeed, I mentioned the concept of using they transmit on their pilot tones with BPSK. They flip the phase around. And since you know the phase is either 0 or 180 degrees, and you know what the magnitude is supposed to be, you can use that kind of as a pilot tone, right? You can use that as a fine-grained pilot tone. Yes? Yes?
We were getting to like Hilbert-Klein transformations or anything like that?
I have no idea what a Hilbert whatever transformation is. This is the part where real radio experts go, oh yes, I know what that is. And I go, I spent many, many years slowly accreting these data in my brain from Wikipedia. You can do it too, but you will not know what a Hilbert-Klein transformation is at the end. Yes?
Any other places or things you recommend?
Other resources. The DVB-T spec, I was going to say is surprisingly readable, but it isn't really. But it is written. It's better. It's better than a 3GPP spec, which is not saying much. Like, it's better than a cell radio spec. And it gives an example of a real system by which they do this. And it suffers from a good amount of like LaTeX, right, on the page. But it does, that is a paper that exists. So I don't know. I would maybe say like go look at GNU radio code, but I'm not sure. My best guess, I'm getting nods of no in the audience, so I don't really know. If you find great resources, tell you what, send me an email and I'll add them to that page. Okay, I think I'm going to declare, since with or without the alternative Josh here, I am declaring that we have hit the hour and 2-minute mark, and so we are done. But you are free to find me later. Thank you.